So, this is the third lecture on Ganitakaumudi of Narayana Pandita. As you can see, the lectures on magic squares are also essentially on the last chapter of Narayana Pandita's Ganitakaumudi. So, Ganitakaumudi is written around in 1356. We do not know where Narayana Pandita lived. Majority of his manuscripts are found in western India, Gujarat, Rajasthan, etc., but maybe he was even in Bihar or somewhere. Or Ganitakaumudi has 475 sutra verses and 395 udaharana verses. So, it is about 4 times the size of Leelavati, and it is divided into 14 chapters. It was outlined in the previous talk also. It is good to recollect them: weights and measures, partnership, sales, interest, etc., sequences and series, geometry of planar figures, which is one of the major chapters in the Ganitakaumudi, 149 rules and 94 examples. It is almost 1/3 of the number of rules are there. Excavation, stacks, mounds of grain, the shadow problems. After that, Kuttaka, Varga Prakriti, then factorization, Bhagadana, Rupadyamshavatara, partitioning of unity into various fractions. They are very interesting results. Most of them go back to Ganita Sar Sangraha actually. Anka Pasha, combinatorics, then Bhadra Ganita, magic squares. So, combinatorics is the next major chapter after Kshetra Ganita, 97 rules. Bhadra Ganita has 60 rules. Narayana Pandita has written his own commentary, Vasana, like Bhaskara did, but it is only on solutions of the examples that he deals with. So, I will be mainly discussing Varga Prakriti, Bhagadana, Anka Pasha in this talk. In the other talk on magic squares, Narayana's contributions in this chapter on Bhadra Ganita will be discussed in detail. So, Narayana brings in Chakravala also into Ganitakaumudi. Ganitakaumudi, as you know, is a party Ganita text. So, it is basically arithmetic and geometry. Leelavati was also party Ganita text, but Bhaskara brought in Kuttaka into Leelavati. Kuttaka is the Brahmagupta thought of. Kuttaka was the generic name Brahmagupta used for whole of algebra, but Bhaskara brought in Kuttaka as a chapter in Leelavati, and his discussion of Kuttaka in Leelavati is same as what he has discussed about Kuttaka in his Bijaganita also. And the idea was that the Kuttaka problem, one does not need to use algebra symbols. Once one knows the Kuttaka algorithm, one only deals with numbers and work out the solution of the indeterminate equation, and the indeterminate equation is also posed as a problem to start with. So, one does not need to do algebra. Similarly, Narayana Pandita has brought in Varga Prakriti into the Party Ganita text. So, he has written a separate book on algebra called Bijaganita Vatamsa. Unfortunately, only the first few chapters of it are available. What is available is only up to Chakravala, and a little bit of the Ekavarna Samikarana is available. So, all the further discussion on Anekavarna Samikarana, etc., it would have been perhaps as much of a expansion of Bhaskara's Bijaganita. His Bijaganita Vatamsa would have been very valuable if the full manuscript were found. So, his description of Chakravala is more or less similar to what Bhaskara has said, but he leaves this issue whether this pi plus 1 squared should be greater than d or should be less than d in a more ambiguous manner in the statement of Chakravala. So, again we want to solve the equation x squared minus dy squared is equal to 1. So, in the step xi squared minus dy squared is equal to ki, you want to obtain pi plus 1. So, you obtain pi plus 1 by solving the Kuttaka problem. Yi plus 1 is equal to yi pi plus 1 xi by ki. So, pi plus 1 and yi plus 1 are not known, yi, xi and ki are already known integers. So, there are 2 unknowns, it is a standard Kuttaka problem. Then once pi plus 1 is found, there are many solutions to Kuttaka. So, you choose the solution such that p squared minus d by k or d minus p squared by k is small. So, ki plus 1, which is pi plus 1 squared minus d by ki, or d minus pi plus 1 squared by ki, and so in the other case kshepa will be negative. So, here just said pi plus 1 squared may be chosen to be greater than or lesser than d, and then of course xi plus 1 is related to the known quantities. Now, what actually Narayana meant by his condition we can understand by looking at the examples that he has worked out. So, he has worked out, as you see, the examples are given in Ganitakaumudi, the solution is discussed by in his Vasana commentary. So, by putting them together you can find out what Narayana intended to do. So, first example is 103. So, in this example again more or less you start with 10 for x and y, then you put k is equal to 1, p is equal to 0, and go by the same method which I think discussed now about 7-8 times, but it does not matter, we can do it once more. So, 0 plus 10 is divisible by 1 and 10 square is closest to 100, and then this 3 is obtained by taking 10 squared minus 103 by 1, you get minus 3. Immediately the solutions are 10 and 1. And the next step, to 10 a quantity should be added such that the sum is divisible by 3. So, 10 plus 11, you could have had 10 plus 8, you could have had 10 plus 14. So, between 8 or 11 or 14, it is 11 whose square is closest to 103, again the same thing. So, you choose 11, once you choose 11, 11 squared minus 103 by minus 3 is minus 6, 11 squared minus 103 is 121 minus 103, it is 18, 18 divided by minus 6 is minus 3 is minus 6. So, in this stage you have 71 squared minus 103 into 7 squared is minus 6. So, you proceed like that and you can stop at the point where you get k is equal to 2 at the step 4, 477 squared minus 103 into 47 squared is equal to 2, and so you can do bhavana and immediately go to the final solution which is 227528, 22419. Of course, if you went through the Chakrawala you would have obtained the same thing. So, in this example there is no distinction between the way Bhaskara would have done and in the way Narayana has done the example. So, his procedure seems to be the same, but it is not so simple. Narayana has worked out another example, and this example is x squared minus 97y squared is equal to 1. This example throws up many interesting features. So, instead of explaining the starting step which is known, second step which is also similar, in this step from 11 to 13 is a very interesting feature to start with. So, in this step your P2 is 11, and so you are at the stage where 69 squared minus 97 into 7 squared is equal to 8. So, you are in this stage. So, now to 11 you add a number such that 11 plus that number is divisible by 8. So, 11 plus 5 is possible, 11 plus 13 is possible, then 11 plus 21 is possible. 5 squared is 25, 97 minus 25 is 72, 13 squared is 169, 169 minus 97 is also 72. So, it is the first time where you are finding an ambiguity. Pi plus 1 squared when it is taken above d or below d is equidistant from the d. So, what do you do? Bhaskara is silent on it. Now, in this example Narayana has just given said that you take the larger one. In fact, Krishna Swami Iyengar in his analysis also has given an algorithm where you are choosing the larger one. So, both 5 and 13, the squares of both these numbers are equidistant from 97. You could have gone ahead and made a rule that you choose the lower one also, you will immediately eventually you will lead to the proper solution of the Varga Prakriti equation. So, this was one thing which was interesting. Now, the second thing is even more interesting, the step from 3 to 4. So, to 13 you add a number such that the sum is divisible by 9. So, to 13 what are all the numbers you can add? 13 plus 5 is divisible, 13 plus 14 and 13 plus 23. Now, 5 squared is 25, 14 squared is 196, 23 squared is 529. Now, your number is 97. So, if you proceed the Bhaskara way, you can see that 25 is closer to 97 than 196, right. So, if you had gone the Bhaskara way, at this stage you would have had to put 5, nothing would have been lost. I mean, eventually you will get the solution, it is just the specification of the algorithm. But Narayana is saying no, we are going to take 14 here. Now, is there something interesting about 14? Now, what is the solution at this stage? Till now we have the solution is 69 by 7. 69 by 7 is telling you various steps are what? 10 by 1. Then the next approximation is 69 by 7. These are all better and better approximation to square root of 97, 197 by 20, right. So, it's actually it is of the order of 9.85, right. Root 97 is of the order of 9.85. Why I am saying this you will understand in a minute. You try to find out or you try to find out. So, I will just take the modulus here. In this situation, if you take 5, okay, root 97 is of the order of, we have seen it is 9.85. So, mod 5 minus root d is of the order of 4.9. Mod 14 minus root d, let us write it exactly. Why write root d here? What is this? Is of the order of 4.1.
So, but at this point we haven't reached there, isn't it? We should still be taking 69 upon 7 as the
no, you can take 69 upon 7. How different? How much is it different? 9.7.8, 9.8. Anyway, you need to know that it is more than 9.5 or less than 9.5. If it is more than 9.5, this is closer to 14 is closer to root d. If it is more than 9.5, this is farther away from root d. So, if your condition is this is the least, then you pick this. If your condition is so, you will get P4, the step we are doing is P4 is equal to 5 is equal to 14 in this case, P4 is equal to 5 in this case. Do you understand what I am saying? So, if you are, this is the Bhaskara condition. Narayana in this step is choosing this condition, which if you implement continuously, it leads to a continued fraction known as the nearest integer continued fraction. This is the nearest integer continued fraction algorithm. So, what Narayana seems to be doing in this example of 97, this is the only place where it differs, otherwise because these two conditions are really very close to each other, only rarely you will find them deviating from each other, the solution being different from each other, and therefore, in this example Narayana is hinting that you can use the nearest integer algorithm, you can use this as the condition for Chakravarti instead of this. So, by this Narayana is just opening up that the Chakravarti process is indeed a process where you can discover several kinds of algorithms, and Bhaskara's algorithm is one such, which is very specific of course. He is hinting that another kind of, by giving these examples he is not making much more statement than that, but his definition of Chakravarti was also in such a way that he did not say this condition unambiguously. He just said that this pi plus 1 should be so chosen that its square hovers around d, and so that is the way he has worked it out. The other thing, this is well known, we have talked about it several times, that the solution of Chakravarti gives good approximation to square root of d, and given one approximation you can work out better and better ones by bhavana. Narayana is the first person who has sort of stated it all these very explicitly, and he has taken the example of square root of 10. It so happens for all his geometric acumen, Narayana is using the Jain value of square root of 10 for pi, and so square root of 10 happens to be a important parameter in his geometry. So, he has just worked out 19 and 6 is one solution, If you do bhavana of that with itself, you will get 721 by 228. If you do the bhavana of these two, of this with the other one, you get 27379 by 8658 and so on. So he says you can work out better square roots. He has just made this all this very explicit. Now we come to Narayana's method of factorization. There is something interesting that he does. So to start with, in fact this is the first book in Indian mathematics which seems to talk about the issue of factorization. In Greek mathematics, Euclid's book itself starts by talking about factors and primes and things like that. All that discussion is generally missing in Indian mathematics book. The first time it occurs, but Narayana does bring in something very special when he starts this subject. So one, he says the usual procedure that when you want to factorize the number, you divide it, try dividing it by successive achhedyas. This is the name he calls to primes, numbers which are not divisible. Achhedyas 2, 3, 5, 7 divided. This is the well known sieve of Eratosthenes or whatever. This is the standard method for trying to find the factors of a number. Then he comes with the following interesting methods. I will skip the Sanskrit. First method he is saying is, if n is a non-square positive integer, find a square integer such that n plus k square is also square. Then n is equal to b plus k into b minus k. Of course, if you succeed then it is well and good. If you do not succeed, this is somewhat simplistic. Then second method, n is a number you want to factorize. So the first starting method was you start with the 2, 3, 5, 7, go on dividing. It so happens that when your first factor itself is very high, how high it can be? The lowest factor, a number n which is not prime, is of the order of root n. So it can become fairly high. So you are thinking of factors which are fairly high, that is when these methods come important. So the next one is, think of n as a squared plus r. So take out the nearest square from it. Suppose it happens that 2a plus 1 minus r is a square. Suppose it happens, then of course n is equal to a plus 1 plus b into a plus 1 minus b. Again it is a lucky chance, it may happen, it may not happen. Now Narayana comes with the sort of an algorithm, what you can try and do. Of course it is not a simple thing, factorization as all of you know is indeed a difficult problem, but Narayana is giving some systematic method when the factors of n are fairly large. So he says keep adding the arithmetic sequence of numbers 2a plus 1, 2a plus 3 with common difference such that their sum minus r, r is that number, a squared plus r, a is obtained by that, such that their sum minus r becomes a perfect square. So that is 2a plus 1 plus 2a plus 3 etc., 2a plus 2m plus 1. So you have gone m terms in this arithmetic sequence, minus r is equal to b square, then n will be a plus m plus 1 plus b, a plus m plus 1 minus b. So this method actually was rediscovered by Fermat. I think Fermat seems to be anticipating, re-anticipating or rediscovering many things that were earlier done in Indian tradition. So Narayana has given two examples, they are not complex, but you can work out more complex examples by what is today known as the Fermat method of factorization. So 1161, so 1161 closest square is 34 square plus 5. Here you are lucky, 2 into 34 plus 1 minus 5 is already a square. So you got factors straight away. Now it is 1001, nearest square is 31 squared he has taken, 31 squared plus 40. Now 2 into 31 plus 1 minus 40 is not a square. So start this arithmetic sequence, cranking it, keep on going, sum as many terms such that those sum minus 40 is a square. So when it happens, you will have a factorization of 1001. You have gone 13 terms in this sequence. So 31 plus 13 plus 1 plus 32, 31 plus. So finally you actually find that 7 itself was a factor. So here there was no need to go and do this, but it is an illustration of the method. So Narayana is the first Indian mathematician to have systematically talked of factorization of a number, and he has come up with an interesting way of attempting it. Now we come to the chapter on combinatorics. It is a very long chapter and actually a very profound chapter. What Narayana Pandita does is he will give a general mathematical formulation to all the combinatorial problems that were earlier considered in the literature, starting from prosody to music and in mathematics. He tries to give a general mathematical formulation. So, in the beginning the chapter starts with defining the various pratyayas that come in combinatorics. So, that is a prastara, a sankhya, an ashta, uddishta, all that, what do they mean. Then he starts by giving auxiliary mathematical quantities. So, he first defines various sequences. So, in the previous talk on Ganitakaumudi there was an exposition of some of this. So, we can continue on that, and merus, that is some tabular figures that are going to be useful in combinatorial problems. So, he defines various kinds of sequences, panktis. Then he starts with the different problems. The way he tries to pose the problem is following. So, in Varnavritta the objects were syllables and they were lagu and guru. In Matravritta the objects were syllables and the objects were lagu and guru. In permutation of Tana Prastara the objects were swara, sarigama, and in Tala Prastara the objects were the talangas, the dhruta, the guru, lagu, pluta. In each case you were putting them in various orders, these objects. So, now he says let me just think of the objects as ankas, digits. So, we will have digits 1 to q. So, these are my objects. So, if it is lagu guru just call them 1 and 2. If it is sarigama call them 1, 2, 3, 4. Of course, in the end of the chapter he says there is a limitation in what I have done. These ankas are only 9 anyway, but you can think of larger ways of doing it, okay, in the end of the chapter. But you think of this. So, the objects are 1 to q and there are some p places, sthanas. So, there are p sthanas in which you place them and then you put various conditions, whether the sum of all the ankas should be constant or whether all the ankas should come only once or whether the sum of the ankas need not be constant, but the number of places is fixed. So, each of them comes to give you different problems. So, in the Varnavritta the number of places is fixed, in the 3 syllable prastara, 4 syllable prastara, 5 syllable prastara, in each prastara there is a particular p which is fixed and the objects in Varnavritta was lagu and guru only. Narayana says we can generalize it, you can think of pluta which is the longer syllable than lagu and guru, you can have anyway q syllables. So, in the Varnavritta problem finally you came up with binary numbers. Now, the representation that will come is a representation of every number to base q or radix q. So, that will be the generalization of the Varnavritta problem. Now, permutation anyway 1 to q are kept in q places and then they can be permuted. Then permutations with repetitions also. Matravritta problem, p is not fixed, 1 to q are placed, repetitions are allowed, sum is a constant, that is the value in Matravritta, the total matras. Tala Prastara also will come in that. Only one thing will not come, Sharngadeva's generalization of 1, 2, 4, 6 will not come, because he is considering all integers sequentially, all ankas sequentially from 1 to q. So, this is the mathematical formulation of all the known Prastara problems in terms of digits. So, q digits, p places, Prastaras are done under various conditions. So, the first Prastara is a permutation without repetition, then he considers Prastara of permutations with where digits are repeated. Next he considers the Prastara which is a generalization of the Varnavritta. So, where instead of lagu and guru there can be other kinds of syllables, pluta etc. So, in general say q types of syllables 1 to q, and this leads him to a theory of representation of each natural number as a polynomial in base q or radix q, which is a generalization of the binary representation of finger. So, he is just working on all this as a mathematician, giving a complete mathematical framework for all the combinatoric problems. Then he goes to Matra Vrittas. So, here again instead of Lagu and Guru, which have value 1 and 2, you think of more different kinds of syllables which have values 3, 4 etc. up to q. Then finally, so this is similar to Matra Vritta Prastara and Tala Prastara also, but it does not subsume the Shangadeva's Tala Prastara. Finally, he discusses Prastara of combinations also. I will deal with that in the end. So, first I will deal with this generalized Matra Vrittas for 5-10 minutes, then we will look at the other things. So, he refers to generalized Matra Vrittas as Niyata Yoga, that is the sum of the digits after I place them in these p places, that should be fixed. Niyata Antimanka, so the final digit is q, some fixed one like that. So, if you want only Lagu and Guru, the final digit is 2. If you want Lagu, Guru, Pluta, final digit is 3. More generalization, you can go up to q. Niyata Antimanka, Aniyata Sthana, the number of places can be many, because even in a Prastara of value 3, you can have 3 Lagus which take 3 places, or a Lagu and Guru which take only 2 places, right. So, Sthana is Aniyata, Bhedanena, Niyata Yoga, Aniyata Sthana, Niyata Antimanka, Bhedanena. In his formulation he has put this, the Matra Vritta Prastara. Then the rule for Prastara is standard, only he extols Bharata. This is the rule for Prastara as declared by the ancients, well versed Bharatagnyaihi Puratanaihi Prastaroyam Samakhyatha. So, the rule is exactly what we had done earlier. Let us look at this example and understand the truth. So, the Prastara where the total value is 7, highest digit is 3. So, you can think of it as Lagu, Guru and Pluta. 1 is Lagu, 2 is Guru, 3 is Pluta. The total sum is fixed, that is 7 now. So, you start with maximum of 3, 3, 1. What is the rule for Matra Vritta Prastara? From the left you start, the first place where 3 non 1 digit occurs, you put the digit just below that, below 3 you put 2, bring down this 3 as it is. Now fill it up, 3 plus 2, 5 is already done, so you can only put a 2 there. So, next step, below this 2 you will have a 1, 2, 3 is brought down, you can only put a 1 there. Next step, below this 2 a 1 will come, 3 can be brought down, only a 3 can be put in the left. Like that you go on, you will see that you have about 7 such rows which have 3 as the last entry, that is followed by about 13 rows which have 2 as the last entry, that is followed by the rest of the rows which is about 22 plus 2, 24 rows which have 1 as the last entry. So, this is the Prastara. This is actually 7 Matra Vritta Prastara with Lagu, Guru, Pluta. The same rule for Matra Vrittas that we did earlier, only we have instead of Lagu and Guru you have also a Pluta, there is no change in there. Now, to understand the Sankhya of this, we go back in the beginning of the chapter itself, Narayana has discussed various sequences. So, we will go back to this Samasiki Pankti, this was discussed in the last class. So, let us look at it once again. Ekankau vinyasya prathamam tat samyutim puro vilikhet utkramato antima tulya sthana yutim tat purastacha antima tulya sthana bhave tat samyutim purastacha evam saika samasa sthanaha samasikiyam syat. So, first 2 Samasiki Pankti consists of 1 and 2 elements of this sequence are just 1. Then up to the value q, the SRQ will be sum of whatever are the previous elements which have come in the sequence. Beyond q, each element of the sequence is a sum of the previous q entries. So, this is the qth order generalization of the Virahanka sequence, as we should call, or what is generally known as the Fibonacci sequence. S1q and S2q is 1, SRQ is sum from S1 to SR minus 1 when R is less than q, SNQ So, when you put q is equal to 2, you will get Virahanka sequence, the Fibonacci sequence. When you put q 3, this is what you will get. When you put q is equal to 3, you will get 1 1 2 4 7 13 24 44. You can see that they were there in that Prasada. There were 7 rows with value 6, there were 13 rows with value 5, and there were, I am sorry, there were 7 rows with value 4, 13 rows with value 5, 24 rows with value 6. In the right, to the right of the first 7 rows you put a 3, to the right of the next 13 rows you put a 2, to the right of the last 24 rows you put a 1. That way you generated that 47 row Prastara, the 7 Matra Vritta Prastara with 1 2 3. So, these are the generalized Virahanka numbers of order 3. This is called the Samasiki Pankti. He defines it right in the beginning of the chapter, where it has nothing to do with the problem of combinations or Prastara. He just defines it generally. This is the general definition, which is that each number is the sum of the previous q numbers after certain point. Now, this is the another Pankti which was also referred to in the previous task. This is called the Suchi Pankti, it is called the needle sequence. Antimamita Vaishlesha Sthanankamitaschya Taha Prithak Sthapyaha Tasam Ghataha Suchi Panktihi Narachika Vasyat. It is also called the arrow sequence or the Narachika Pankti. So, 2 names for that. So, how it is to be done? You first do the Vaishleshiki Pankti, which he has defined earlier, that is put just 1 next to itself q times. 1 is put next to itself q times, that is called the Vaishleshiki Pankti. Then you multiply that by itself p times. The elements of the Narachika Pankti will come. And the method of multiplication is the algebraic method of multiplication, or what in India is called the door junction Kapata Sandhi method. So, let us first see that. So, p is equal to 3, q is equal to 3, the Vaishleshiki Pankti is 1 1 1. So, first you multiply it by itself. When you multiply it by itself, you get this kind 1 1 1 1 1 1 and 1 1 1. So, you add this, you will get 1 2 3 2 1. So, this is the square of 1 1 1. You do it once more, you get the cube of 1 1 1, that is 1 3 6 7 6 3 1. So, you can see each term here is a coefficient in 1 plus x square to the power 3, coefficient of different powers of x in 1 plus x square to the power 3. This 1 3 6 7 6 3 1 is Samasiki, is the Narachika Pankti or the Suchi Pankti when p is equal to 3, q is equal to 3. So, like that he defines. So, in general the needle sequence is given by just slightly different notation than the previous talk. U, P, P, Q are put as arguments of u, I have put them as subscripts here. So, u, P, Q of r is the coefficient of x to the power r in 1 plus x squared plus x to the power q minus 1 whole to the power p. As was emphasized by Professor Sriram, Narayana Pandita does not define it in this manner, but what he is saying is an algebraic definition. He says you take this Vaishleshiki Pankti, multiply it by itself by Kapata Sandhi method, that means treat it as a polynomial and multiply. Okay. This what is the interesting thing about this Suchi Pankti is that beautiful relation which was also defined in the previous talk. So, this occurs in context of Matra Vrittas. I will explain the relation in a minute. Before that, what Narayana Pandita does is he defines a tabular figure called Matsya Meru, which we will not display, somewhat complex. Each row of the Matsya Meru is filled by elements of this needle sequence U, P, Q, R. But anyway, the Matsya Meru is given by giving a value of p and a value of q. P is equal to 3, q is equal to 3, p is equal to 5, q is equal to 2, whatever. Then Narayana gives some of the important properties of UPQ of R in the context of the Matsya Meru. While summing the rows of the Matsya Meru, while summing the columns of the Matsya Meru, he gets two important relations. Narachyaha tiryagaha sthana samhitaha tad yutihi prithak gunottara bhavet pankti. So when the rows of the Matsya Meru are summed, you will get gunottara. Gunottara means a geometric sequence. You get a geometric sequence q to the power p. Q is fixed. So when you sum the first row, you will just get q. When you sum the next row, you get q squared. When you sum the third row, you get q cubed. It is something like a multinomial theorem. For q is equal to 2, this will be like the binomial theorem. Then urdhva ankaikya samhitaha prithak tadurdhva khoshtanka yogat samasika bhavet. When you sum the columns of the Matsya Meru, you will get the samasiki pankti, which are the generalized Virahanka numbers that we talked about. So the relation is something like this. Sum of u n minus r q r is equal to 0 to n minus t is the generalized Virahanka number s n q, where t is such that t minus 1 of q is less than tq. So this is the relation between the samasiki pankti and the generalized Virahanka sequence, which is the this is the relation between the Suchi pankti and the samasiki pankti that Narayana is writing. He is thinking, putting everything in the general framework also, and it is fairly abstract and complex, but it is very interesting. Now what is its interpretation for Matra Vritta? SNQ, as we saw, is the Sankhya, that is the number of rows in the Prastada of a Matra Vrittas which are of value n, where the elements, syllabic elements that you can choose have values from 1 to q, or in ordinary language it is the number of rows when you list all the partitions, ordered partitions of number n in terms of 1 to q, where repetitions are also allowed. So that is your Sn of q, that is the generalized Virahanka sequence or the generalized Fibonacci sequence. Now un minus rqr you can show by just simple algebra that it is the total number of generalized Matra Vrittas of value n, where the Vrittas are stipulated to have just length n minus r. When you sum the number of syllables of the Vrittas which are allowed from 0 to that n minus t, you will get the total number of Matra Vrittas of value n. So this is by when Vrittas are fixed length, when you stipulate that the Vrittas are of fixed length, this will be the number of Matra Vrittas of length n minus r of total value n, where 1 to q are the syllabic values that are allowed. Okay. Now Nashta and Uddishta also has to be done, and there also Narayana comes up with a very interesting tabular figure, and this tabular figure is again defined at the beginning of the chapter. This tabular figure is called Unmeru, the lofty Meru. So what is the construction? The bottom row you put the Sankhyankas, the generalized Virahanka sequence 1, 1, 2, 4, 7, 13, 24, 44, when n is equal to 7 and q is equal to 3. When q is equal to 3, you will get this sequence. Now you are looking at the situation where n is equal to 7, put the 8 elements in the bottom row to consider the problem of the Nashta Uddishta problem, because now what is the Nashta Uddishta problem? Nashta Uddishta problem is, we have this Prastara, I want to know where does 1, 1, 2, 1, 2 appear, or I want to know what is the 39th row. This problem I want to solve, and Narayana solves this with the Unmeru. So you put this Sankhyankas 1, 1, 2, 4, 7, 13, 24 bottom, and from the top write 1, 2, 3 to the left. You are considering q is equal to 3, so you write 1, 2, 3 to the left. Now this is the Meru, it has been constructed. Now how do we use it to solve the Nashta problem? So what is the example of Narayana? Find the 36th row of the 7 Matra Prastara with highest digit 3. So you write this whole thing. We want to calculate the 36th row. So what is the process? Start with 44, subtract 36 from it, 8 is left. You can only subtract this 7 from the 8, 1 is left, you can only subtract this 1 from this 1, 0. So, only 7 and 1 are the patitankas, only those two are the fallen numbers, all other numbers are apatita sankhyankas. Okay. Now, you start with the first apatita sankhyanka, go up, mark the first entry that comes there, then go to the top of that row, go left, reach the next apatita sankhyanka, mark that number there, go to the top of that, go to the left, reach the next apatita sankhyanka, mark the number there, go to the top of that, go left, reach the next apatita sankhyanka row, mark that, go to the top of that, go left, mark whatever you get in the next apatita sankhyanka. So, the apatita sankhyanka columns whatever comes, they are all marked. So, your final form is 21211. 21211 should be the 36th row of the 7 matra prastara. So, 36th row is used to identify the patita and apatita sankhyas. So, only two sankhyas are patita, 7 and 1. So, let us see the 36th row. 36th row is 21211. Okay. So, this is Nashta with the Unmeru. Now, Uddishta. What is Uddishta? Given a form, we have to find out the row in which it appears in the prastara. So, again use the Unmeru, put down 1 to 44 here, do the Unmeru. Now, what you do? You have to identify the patita and apatita sankhyankas now using your pattern 2212. So, start from, find out the column in which 2 appears just above the sankhyanka. So, that is this column. So, this will be a apatita sankhyanka, mark that 2, go to the top of that, go to the left till you find the next one, you want 2122 and mark this, this is another apatita. Then go to the top of that, go to the left till you find the next 2 that is here, this is another apatita. Then go to the top of that, go to the end of that till you find the last 2. So, you have found your 2, 2, 1, 2, they are arising in the columns 13, 7, 2 and 1, those are the apatita sankhyankas. The patita sankhya's are the others 13, 7, 2 and I am sorry, the patita sankhya's are the other, those are 24, 4 and 1. So, 44 minus sum of the patitas is 15. So, 2212 should appear in the 15th row of our prastara. So, you can go back and check that. 15th row is 2212. So, there is a much simpler way of doing this Uddishta, following what we did in the case of the Matra Vrittas. We also did the same thing in the Tara Prastara also. So, I will describe the simpler method. So, what do you do? Write the sequence of sankhyankas, but write them in such a way that you write 3 sankhyankas above 3, 2 sankhyankas above 2 and 1 sankhyanka above 1. This is what we had done in the case of Shangadeva. We put 4 sankhyankas above the Pluta, 6 sankhyankas above the Pluta, we put 4 above the Guru, 2 above the Laghu and 1 above the Dhruta. Or in Matra Vrata Prastara, we put 2 sankhyankas, 1 above and 1 below the Guru and 1 sankhyanka only with the Laghu. So, this is just a generalization of that. Write 2 sankhyankas above 2, 3 above 3, 1 above 1. Sum the second and third entries above each 3, second entry above each 2 and subtract that sum from the sankyanka of the prastara, which is 44, to obtain the row number. So, here are 1, 1, 2, 4, 7, 13, 24, 14, 2 are written above 2, another 2 are written above 2, 1 is written above 1, 2 are written above 2. So, only the second entry above 2 is significant and those are the patita sankyankas 24, 4 and 1. So, 44 minus. So, this example we had done just before 2212 we had identified with the 22nd row. So, let us do another example. Find the row in which 322 appears in the 7 matra prastara. So, write 3 sankyankas above 3, 2 sankyankas above 2, 2 above 2. The second and third above 3, the second above 2 are the patita sankyankas, they are 24, 7, 2 and 1. So, you have, so this should be the 10th row 322 should be the 10th row of the Prastara. So, we will again check that 10th row of the Prastara is 3 2 2. Okay. Now, this again gives us another representation. So, what is happening? 8 in our examples, in this example this number 34 is being written as 1, 2, 7 and 24. It was written as a sum of the generalized Virahanka numbers. In the earlier examples we had written 8 as sum of 1 and 7, 29 as sum of 1, 4 and 24. So, we can see another general theorem is behind. The theorem is something like this, that every number is either a generalized Virahanka number or it can be written uniquely as a sum of the generalized Virahanka numbers, with the condition that q consecutive Virahanka numbers will not appear in this sum. So, when q is equal to 2, 2 consecutive Fibonacci numbers will not appear. When q is equal to 3, 3 consecutive Virahanka numbers will not appear. So, like that. So, this is the general result which is behind this Unmeru and this Nashta and Uddishta process. Now, next thing is interesting thing is Narayana does this Prastara where the swaras can be repeated. So, this is like Sasa Ri Ma, this is the Prastara of Sasa Ri Ma. So, what is the rule for Prastara? You just follow Sharngadeva's rule, you will get the Prastara of this also. So, you start with 1 1 2 4, wherever there is an ascent 1 2, you put below 2 the next one, that is 1, bring down the right things as they are, whatever remains you put in the ascending order. So, it is 1 2 1 4. Now, 1 2 is in ascending order, below the 2 you put 1, bring down the 1 4 as it is, whatever is left is 2. Now, 2 1 1 4, only 1 4 it is in ascending order. So, below this 4 you have to bring down a 2. Now, the rest of the numbers have to be put in ascending order. So, wherever repetition occurs, repetition will come. So, this is the way you generate all possible permutations of q quantities where they are repeated also. Of course, the Sankhyankas here, the total number of permutations or the total number of rows in this Prastara will be this multinomial or 4 factorial by 2 factorial, and the method of Sharngadeva just goes through. Narayana Pandita is the first person to have listed the permutations with repetitions. They are called multisets. This theory is itself fairly interesting. Finally, Prastara of combinations. So, what is a Prastara of combination? Basically, we will take an example first and then go back to the theory. So, you have 8 digits, choose 3 of them. How many ways you can do? C8 3, that is 8 factorial by 5 factorial into 3 factorial, that is 56. So, C8 3 stands for number of combination, that is the usual. I am using this notation instead of NCR, I am using this notation CNR, okay, simpler to type. So, here you see all such combinations are ordered in a sequence. So, you are having a rule for Prastara, and once you have rule for Prastara, you have Nashta, Uddishta, and you also have ultimately a representation of every row number in terms of certain Sankhyas. So, all that theory will come, we will not go into details of this. No, there the sum is constant. Here you are taking combinations. Here you are listing all possible combinations which arise when you choose 3 objects from 8 objects. So, here you see each row is just 3 entries. Their sum is anything, their sum is not at all fixed. Talangas is the total tala amount is fixed. This is a very different kind of, this is permutation, this is Prastara of combinations. This is generating all possible combinations in a sequence. So, the rule is, it is written in a fairly slick fashion, Nyasya alpam adyan mahato adhastat shesham yathopari une tad utkramat ankan ekaikonan samalikhet chaya panktihi bhavet yavat tavat prastarajo vidhi. So, the last row should become 1 2 3, that is the simplest arithmetic sequence. Start with the highest arithmetic sequence. So, the rule is the following: from the left, whenever you find something below that can be written, you write that and bring down the right things as they are. So, this will go on till this point. Now below 7 you have to write the number just below that if it is not found to the left of this, that is the rule. So you can put your 6 here, 8 is brought down. Now with the 6 you write only the sequence of numbers next to it to the left. So this rule I have written down in a complex manner here. The first row of the Prasada is given by the sequence of symbols n minus r plus 1, n minus r plus 2 etc. n. To go from any row to the next row, scan it from the left, and the first entry I greater than 0 such that I minus 1 does not appear earlier in the row, place the symbol I minus 1 there, bring down the right things as they are. This in any Prasada, that is one of the standard refrain. To the left place the symbols I minus 2, I minus 3 in order till the next row has also R symbols. By this process you will generate all the combinations. And there is another interesting physical way in which Narayana says this Prasada can be done. It is called Ladduka Chalana or Loshta Chalana. This was briefly hinted by Varahamihira in his half a verse that I mentioned in the case of the 16 perfumes. So the rule is like this. Let us look at this diagram. Keep these laddus here. Rule is from the left, the first laddu which can be moved to the right, move that to the right. Leave whatever else is to the right as it is. If there is something else to the left, bring them down back to the beginning. So laddu chalana, let us begin. We put 3 laddus here. First this will go there. Next, so from the left this can be moved right. So I do that. Right should be left as it is. Left cannot be moved any further left. So it simply stays there. So in this row, from the left this laddu can be moved. So move this. And right, nothing else is to be done. So you are there. Now we are here. From the left the first laddu can be moved is what is there here. So that can be moved to the right. So that is brought here. These 2 laddus, take it to the left extreme, take it to the left extreme. So like that go on and on and on. Ladduka Chalana, and in the end you will come with this. Now only thing is this is starting with 1 2 3 and ending with 5 6 7 8. So it is Prasada in the reverse. So he also mentions that you can use this Ladduka Chalana method to do Nashta and Uddishta. Is just brilliant the way they are thinking about the problems in multifarious ways and putting them together. And from this we can generate something called as a representation of every integer in terms of the binomial coefficients. We will not go into the theory of this. So I will just write down. So each number 5 can be written as a combination of the binomial coefficients in a unique manner. For any given Prasada such a representation is possible. So as I said, the theory of combinatorics always has this representation associated with this. Theory of combinatorics means writing things in an array as a Prasada, then associating with the row numbers the patterns which occurred in the Prasada in that row, associating the patterns with the row number. So ultimately you will end up with a representation of numbers in terms of other interesting numbers which are associated with the Prasada, do the Sankhya. So this is a very general method which goes back to Pingala, and Narayana almost has brought it to a beautiful mathematical perfection. So in the end he does say that my theory is limited by the fact that the number of ankas that are there has to be less than or equal to 9, but intelligent people can devise ways by which they can do this problem. So Ganitakaumudi was edited by Padmakar Dwivedi in 1936 and 42 in 2 volumes. These combinatorics and magic square chapters were extensively studied by Kusuba in a thesis from Brown University under Professor Pingree. It has been translated by Professor Parmanand Singh in issues of Ganita Bharati. It is a good introduction to understanding. Then there are some articles on particular topics. Thank you very much.